Okay, we have Saeid Nezamabadi from Montpellier talking about packing of hexapod particles.
Okay.
Yes.
Okay. Okay, thank you. Good morning. First, I'm sorry I couldn't be there in person. I would like to thank the organizers for giving me this chance to present our research work entitled Packing Properties of Hexapod Particles. Indeed, this work was done with the collaboration of the French Alternative Energies and Atomic Commission, Energy Commission, CEA, in the framework of the PhD thesis of Louis Tran with Jean-Philippe Bay from CEA and Farhang Ajayi from LMGC that you have seen his presentation yesterday. Sorry. Okay. Granulation is a very common process in many industrial processes. You can see here an example of dioxide of uranium nuclear powder, which is composed of aggregates made of primary particles with the dendrite shapes. And you have many sizes also, different sizes. The crucial point about agglomerates is their strength. It should be sufficiently high to avoid the destruction during different processes. The strength depends principally on cohesive interactions, sizes and shapes of primary particles, and also the agglomeration process, which controls the microstructure and the porosity of the agglomerates. In this study, we focus on the effect of particle shapes on the aggregate strengths. Particle shape affects the packing and mechanical properties. We studied different particle shapes such as hexapod particles or platelet particles. However, in this talk, I will focus on hexapod particle, which can say that is it can represent the dendritic structures of, for example, U2 powder that you have seen before. Our DEM simulations were performed using a homemade code called Radial, like the Farhang presentation yesterday. The hexapod particles are defined as three mutually orthogonal cylinders with spherical caps. The shapes of the hexapod is defined by its aspect ratio, alpha, a ratio of the length of each lobes to its thickness. Equivalently, we define the parameter eta, which varies between 0 and 1. 0, we can say that corresponds to a sphere, and 1 to infinity thin hexapods. So here you can see the hexapods of different values alpha varying from 1 to 9, and you can see it vary from 0 until 0.99. In simulations, we kept L constant and we changed H to get the desired aspect ratio. To create the aggregates, performed first a radial compaction. The hexapod particles are placed randomly inside a spherical ball, and a radial dynamic compaction is applied under a constant pressure until the particle gets jammed in a stable configuration. In this process, the friction is set to 0, and the pressure P is low as compared to contact stiffness. Here you can see an example of radial compaction for alpha equal to 4 and more than 8,000 particles. Here you see the evolution of the average number of neighbors, Z, per particle, and the average number of contacts per particle, ZC, and the packing fraction during compaction. For alpha equal to 4. As you see, the value of these quantities are stabilized in a fraction of seconds. In the following, I will consider the dependence of these quantities on the hexapod ratio. So, for example, these curves show the packing fraction as a function of eta, the last value of packing fraction that you have seen before. So, for the sphere, eta equal to 0, the packing fraction is approximately 0.63, sorry, corresponding to the random closed packing space. As eta increases, the packing fraction increases mostly, passes by peak at eta equal to 0.5 approximately, and then declines as the hexapods become thinner and thinner, and as you can see here. This unmonotonic behavior has also observed for other particle shapes. It is remarkable that this unmonotonic evolution of phi with eta can be fitted by a third order polynomial, you can see here, with involving two terms, eta squared with a positive coefficient, and beta and eta cubed with a negative coefficient. Eta squared indeed represents the interlocking effect in the sense of that the lobes cross each other and can have the contacts closer to the center of the hexapods, for example, for these cases. And eta cube represents a strict exclusion between particles. So hence the packing fraction increases with eta squared and decreases with eta cube. You see here the coordination number Z and the contact number ZC as a function of eta, the shape parameter. ZC is equal to its isostatic value for a sphere at eta equal to 0, as you can see here. That it jumps to 12, which is the isostatic value for our spherical shapes. It keeps its value nearly equal to 12, except for alpha equal to 3, here, as you can see, where it is higher than 12. We will see why on the next slide we have this behavior. For Z, of course, the coordination number is smaller than the contact number because two hexapods can have more than one contact. Z increases slightly with eta, but for larger values of eta, it begins increase much more. The reason is that beyond this point, we can say the 0.66 corresponding to alpha equal to 3, the hexapods are thin enough to touch their second neighbor. Regarding the case of alpha equal to 3, we have seen that the contact number is higher than 12, we have seen before. So this is actually due to high sensitivity of local structure composed of hexapods with alpha equal to 3 to the confining pressure. On this graph, as you can see, you see that as pressure is decreased, ZC decreases towards 12, while Z keeps approximately the same value. It's the same. So the average number of neighbors remains constant, but the number of contacts change. Here you see the hexapods that have more than 16 contacts for alpha equal to 2, 3, and 5. We see that the particles make large cluster in the case of alpha equal to 3. This shows that the hexapod with the aspect ratio 3 tend to make locally ordered structure composed of parallel hexapods. You can see here this is an example of this spontaneous ordering of nearly parallel hexapods. You can see that we have only 2 particles in red, but we have many particles, several particles in blue. Here you see the distribution of distance L between the centers of hexapods for different values of alpha. They are normalized by D. D is the length of a lobe. We see that the distribution are tight for low values of alpha, as you can see here, and they get larger as alpha increases. You can see high value of alpha. the peak values are close. For this case, at the beginning, the peak values are close to the minimum distance. This means that most hexapods are interlocked at the closest distance. Then the interesting point here is that behind alpha equal to 3 is here, yeah, is here. The distribution gets much broader, and the peak value is more close to minimum. This is a consequence of contacts with second neighbor. This curve shows the average distance as a function of shape parameter eta. The average decreases smoothly, and its value can be used as a measure of interlocking between hexapods. We also looked at the bulk modulus, which is normalized by E star. This is defined from the contact stiffness Kn and the average intercenter distance between hexapods. If we do not consider the case of eta equal to 0, as you can see here for the spheres, we see that the bulk modulus is a decreasing function of aspect ratio, as you can see here. The curve is close to its estimate from the effective medium theory. This is the black curve, you can see it. So from this X expression, we can say that the decrease of bulk modulus is mainly due to decrease of L square, if you look at in this equation. Now, to see the effect of the microstructure on the mechanical behavior, we made the agglomerates cohesive and subjected them to the diametrical compression between two platens. So to create the cohesive agglomerate, we removed the compacting sphere that we had before and added an irreversible cohesion force. This is irreversible, and to all contacts between hexapods. So a contact can exist to a tensile strength equal to Fc. We also added here, for example, we added a coefficient of friction of mu equal to 2. And we say, for example, with this example, we take sigma c 0.5 megapascal. After adding the cohesion, the addition force and the friction force, we let the agglomerate relax, and generally the structure does not change much during relaxation. So the agglomerate is then placed between two platens, and the base is fixed, as you can see here, and the top platen is moved downward at a constant velocity. Here you see a video from a geometrical test, top view and side view. The forces are represented by lines joining hexapod centers and of thickness equal to the normal force. Blue lines are attractive forces due to cohesion, and the red lines are repulsive forces. You can see here the breakage area. Here you see the evolution of stress defined by dividing the force experienced by the platens on the largest cross section of the agglomerate. The stress is normalized by the cohesive stress, as you can see, for different values of all values alpha that we have. So here the coefficient of friction is 0.2 and sigma c is 0.5 megapascal. We see that the compressive stress increases up to a peak value for all value of alpha, you can see, and decreases as a result of the breakage of the agglomerate. The peak value increases with aspect ratio. So you can see here better this effect. Here we have plotted the peak value, which represent the strength of the agglomerate as a function of eta. The stress increases slowly with eta up to eta about 0.67, which corresponds to alpha equal to 3. And then it increases dramatically with eta, as you can see here, multiplied by 10 or 12. This is a logarithmic scale. we saw this change in the microstructure property. We can therefore attribute this geometric increase of the strength to a much stronger interlocking of hexapods, and more specifically to the contacts with second neighbors. Here we also see that while the effects of friction is very small in the case of a sphere, the tricle-de-jour, you can see here, its effects become increasingly important with eta. So this shows that friction plays also a crucial role in the cohesive strength of hexapods. In summary, we could characterize aggregates composed of hexapods in terms of packing parameters like packing fractions, interlocking, and contact number, and mechanical properties like modulus. The structure properties evolve with aspect ratio. We see that behind a specific value of the aspect ratio, interlocking prevails and the cohesive strength is amplified. Also, we want to extend these works to investigate other particle shapes, like the platelet, as you saw before, or also mixture of different particle shapes. We hope we can validate, experimentally these numerical results. We would like to perform the simulations of packing of agglomerates to investigate the flow of agglomerates and their breakage during the flow. Thank you very much for your attention.
Thank you, Saeid. So we have some time, a couple of minutes. Question? So I cannot. Can you hear me, Saeid?
Yeah.
Yeah. So I can ask a quick question. So you're in your mechanical experiment, when you have this platen force, plates pushing the particle, and you have cohesive and so you have attractive and repulsive forces there. So these forces that you categorize, they are due to the geometry of the particles mostly, or there is actually intrinsic cohesion between particles as well?
In fact, indeed, yeah. This is the force. The force that if it's the negative force, you have the attractive force. It means if you have the positive force, this is the repulsive forces here. You can say the normal forces. So the intensity of the forces shows here with the thickness of the lines here. So this is the lines that connect the center of the particles. So the red one is the repulsive. So you can see that at the beginning, if you look at the beginning, we have only the cohesive force. After that, we start to have the repulsive force that start to break, as you can see.
Thank you. There are no questions, and we might wrap up and go for coffee. Yes.
Okay, thank you.
Well, thank you very much.